Right now, more than 15 billion miles from the sun, a radio signal is leaving a spacecraft roughly the size of a small car and beginning a journey that takes about 23 hours just to reach Earth. When it finally arrives at a deep space network dish in the California desert, it will be almost nothing, something like 1/10,000,000th of 1/1000,000th of a watt, roughly 20 billion times weaker than the power it takes to run a digital wristwatch. The spacecraft sending it was built for a 5-year mission. It has been flying for nearly 49, but the strange part is not that Voyager 1 is still talking. Everyone expected the radio to outlast the science. The strange part is what the signal has been saying. Because somewhere past the edge of the solar system, Voyager started reporting a condition that half a century of physics said should not exist, and the people who built the instrument are still arguing about why. 3 things are going to matter in this story. The first is a magnetic measurement that was supposed to be a formality, a box to tick, and instead contradicted the model of where the solar system ends. The second is a sound, not a metaphor, an actual persistent signal in the thin gas around the spacecraft that no one designed an instrument to hunt for, and that no one expected to find. The third is a deadline. Voyager 1 is losing power on a schedule you can work out with a pencil, and NASA has already begun switching instruments off one at a time to buy extra years. There is a date when the last one goes dark. There is a date after that, when the radio goes quiet for good. We will get to all 3. But to understand why any of it matters, you have to go back to a mission that was never supposed to leave the solar system in the first place. In 1965, a graduate student named Gary Flandreau was working a summer job at the Jet Propulsion Laboratory in Pasadena, plotting the positions of the outer planets on graph paper. It was tedious work, the kind you hand to the youngest person in the building. And while he was doing it, he noticed that Jupiter, Saturn, Uranus, and Neptune were drifting into a rough line on the same side of the sun, an arrangement that would let a single spacecraft slingshot from one to the next, stealing a little orbital energy at each stop and arriving at the last planet decades earlier than any rocket could manage alone. The alignment comes around roughly once every 176 years. The last time it happened, Thomas Jefferson was president. Flandreau had found it with about a decade of lead time. JPL called it the Grand Tour and asked Congress to fund it. Congress said no. What survived the budget fight was smaller and safer, a mission to Jupiter and Saturn only, officially called Mariner Jupiter-Saturn 77, with a projected lifetime of 5 years. Engineers built the spacecraft to survive 4 years of flight to Saturn, and a little margin after that. Uranus and Neptune were not on the paperwork. Interstellar space was not on the paperwork. Nothing in the design documents contemplated a machine still returning data in the 2020s. The name changed to Voyager a few months before launch. Voyager 2 went up first, on August 20th, 1977, from Cape Canaveral. Voyager 1 followed on September 5th, on a faster trajectory that would let it overtake its twin before Jupiter. 2 spacecraft, a shopping list of 2 planets, and a warranty that would expire before the first Star Wars sequel. Then it reached Jupiter, and the warranty stopped being the interesting number. Voyager 1 made its closest approach to Jupiter on March 5th, 1979. The accepted belief going in was simple and almost universal. Moons are dead. They are cratered rock, geologically finished, frozen in place billions of years ago. Our own moon is the reference case, and it has not done anything interesting since before there were fish. 3 days after the flyby, an engineer named Linda Morbido was working through navigation images, the boring frames taken to confirm the spacecraft knew where it was against the background stars. She brightened one to bring out the faint stars behind the moon EO and found a smudge rising off the edge of the disk, a soft crescent hanging above the surface where nothing should have been. It was a volcanic plume throwing sulfur more than 100 miles above the ground. Io turned out to be the most volcanically violent object in the solar system, and the reason was Jupiter itself, flexing the moon with tidal forces until the interior stayed molten. That single frame rewrote what a moon could be. Every conversation we now have about liquid water under the ice of Europa, about Enceladus venting into space, about whether life needs a star at all, traces back to a smudge on a navigation image that almost nobody was supposed to look at closely. Voyager 1 also found a ring around Jupiter, faint and dark, which nobody had predicted either. And then came the decision that defined the rest of the spacecraft's life. Saturn's moon Titan was the only moon in the solar system known to have a thick atmosphere. Nobody knew what was under the haze. Mission planners wanted a close pass, badly, but the geometry was brutal. The trajectory that swung Voyager 1 past Titan would also fling it upward, out of the flat plane where the planets orbit, on a path that could never reach another world. They took it. On November 12th, 1980, Voyager 1 flew past Titan, found an atmosphere thicker than Earth's, mostly nitrogen, opaque from top to bottom, and then climbed away from the ecliptic plane at an angle of about 35 degrees. Uranus and Neptune went to Voyager 2. Voyager 1 was done with planets forever, 3 years into a 5-year mission, aimed at nothing in particular. For the next decade, it mostly coasted. Then, in 1990, Carl Sagan spent years lobbying NASA to turn the cameras around for one last frame. There was no scientific value in it. The planets would be too small to resolve. He wanted the picture anyway. On February 14th, 1990, Voyager 1 photographed Earth from roughly 4 billion miles away. In the image, the entire planet occupies less than a single pixel, a pale dot caught in a shaft of scattered sunlight. Every person who has ever lived, every war, every empire, every argument, sitting inside a smear of light smaller than the period at the end of a sentence. Then NASA shut the cameras off to save power. They have never been turned back on. The software that ran them has been overwritten. Even if you sent the command today, there's no camera left to answer it. What remained was a set of instruments that measure things you cannot photograph. Magnetic fields, charged particles, plasma waves, invisible physics, sent home at a data rate slower than a 1980s fax machine. And that turned out to be exactly the right cargo for what came next. In December 2004, about 94 times farther from the Sun than Earth is, Voyager 1 crossed something called the termination shock. The Sun throws off a constant wind of charged particles, moving at roughly 1,000,000 miles an hour, and that wind carves out a bubble in the surrounding galaxy. At some distance, the wind slams into the interstellar gas and slows below its own sound speed abruptly, the way water piles up when it hits the bottom of a sink. Voyager 1 flew through that pileup and kept going. Beyond it lay a turbulent zone, then, somewhere out there, the real boundary, the heliopause, the place where the Sun's influence finally loses and the galaxy takes over. Nobody knew how far away it was. Estimates ranged over billions of miles. It took 8 more years. And when the moment came, they could not tell. The instrument that should have called it, the plasma science detector that measures the density of the gas around the spacecraft directly, had failed in 1980. It had been dead for 32 years. So Voyager 1 arrived at the most important boundary in the solar system, with no working way to measure the one quantity that would prove it had crossed. What the spacecraft still had was a plasma wave instrument, which does not measure the gas directly, it listens to it. Charged gas rings at a frequency that depends on how tightly packed it is, the way a wine glass rings at a pitch that depends on how much water is in it, but it only rings when something strikes it. So the team waited for the Sun to hit the gas for them. In March 2012, the Sun threw off a coronal mass ejection, 1 billion tons of charged particles heading outward. 13 months later, in April 2013, that shock wave washed over Voyager 1 and the surrounding plasma rang. The instrument caught the pitch. The frequency indicated a gas roughly 40 times denser than anything Voyager had measured inside the solar bubble, which is precisely what interstellar space is supposed to look like. Don Garnett's team at the University of Iowa ran the numbers backward through the data. The crossing had happened on August 25th, 2012, and they announced it in the autumn of 2013, more than a year late, because the proof had to arrive from the Sun on its own schedule. Voyager 1 had left the solar bubble, first object from Earth to do it. That alone would justify the mission. But here's the part that broke the model. Everyone expected the magnetic field to turn. Inside the bubble, the magnetic field is the Sun's, dragged outward by the solar wind and wound into a spiral by the Sun's rotation. Outside, the field belongs to the galaxy, shaped by everything the Milky Way has been doing for billions of years. 2 completely different fields, generated by completely different things, pointing in completely different directions. Crossing from one to the other should feel like walking from a room where the compass points north into a room where it points somewhere else entirely. The rotation was supposed to be the signature. It was in the textbooks. It was how you would know. Voyager 1 crossed. The field strength roughly doubled exactly as predicted. The direction barely moved. Nearly 14 years later, it still has not moved the way it should. The magnetometer keeps reporting a field that is stronger, denser, unmistakably different in every way, except the one that was supposed to matter most. The best explanations involve the galactic field being draped and bent around the solar bubble, like fabric over a hand, so that near the boundary it lines up with what is underneath it, which may be right. But it means the edge of the solar system is not an edge. It is a smeared, layered, negotiated region, and the model that stood for half a century described a wall that does not exist. That is the first signal NASA did not expect. If this is the kind of thing you want more of, subscribe. This channel covers deep space missions and the physics that comes back from them every week. Now the story gets stranger, because once the team was listening to plasma instead of measuring it, they kept listening. And in 2021, a doctoral student at Cornell named Stella Koch-Ocker went through years of plasma wave data looking underneath the loud events, beneath the solar shocks that everyone had been waiting for. She found something quiet and constant. A faint, narrow, persistent signal, always there at almost the same pitch, month after month. The interstellar gas is humming, not because of the sun, not because of anything the sun did. It is the background state of the galaxy, a low, continuous vibration in the gas between the stars, and until Voyager 1 got far enough out and quiet enough to hear it, nobody knew it was there. No instrument was designed to look for it, because no theory said to look. And it turned out to be useful, because if the gas hums all the time, you can read its density all the time, continuously, without waiting 13 months for a solar storm to arrive and ring the bell for you. A spacecraft that had lost its plasma instrument in 1980 got a replacement measurement 41 years later out of a signal nobody predicted, using hardware built before the Walkman. That is the second signal. The third one is the reason any of this is still happening, and it nearly ended in a way nobody could fix. On November 14th, 2023, Voyager 1 stopped making sense. The carrier signal was fine. The spacecraft was clearly alive, clearly pointed at Earth, clearly executing commands. But the data coming back was a repeating pattern of ones and zeros, the same loop forever, containing nothing. No science, no engineering readouts, no way to ask the spacecraft what was wrong, because the part of the spacecraft that answers questions was the part that had broken. The flight data subsystem packages everything Voyager knows and hands it to the transmitter. It was built in the early 1970s. It holds less than 70 kilobytes of memory, which is roughly one low-resolution photograph, and it is the only voice the spacecraft has. Now consider the working conditions. A command from Earth takes around 22 hours to arrive. The answer takes another 22 hours to come back. Every single thing you try costs you 2 days before you learn whether it did anything at all. There's no reboot. There's no safe mode that fixes this. If you send the wrong instruction to a machine with 70 kilobytes of memory and no undo, you can end the mission with one keystroke, and you will not find out for 45 hours. The people who wrote that software wrote it in the 1970s. Many of them are retired. Some of them are dead. The documentation exists partly as paper in boxes, in handwriting, in the margins of engineering notes, and the team spent weeks reading it. On March 1st, 2024, they tried something close to desperate. They sent a command they nicknamed the Poke, which essentially told the flight data subsystem to stop doing what it was doing and run through its software differently, on the theory that a different path might produce a different failure, and a different failure might be readable. 2 days later, a signal came back that was still not proper data, but it was a different pattern. An engineer at the Deep Space Network spent hours pulling it apart and realized what he was holding. It was a dump of the subsystem's entire memory, the whole 70 kilobytes, sent back raw. They compared it line by line against the version the spacecraft was supposed to be running. A single chip had failed. One chip, holding a slice of the code, gone, taking with it the instructions that assembled every message Voyager sends home. Maybe a cosmic ray hit it. Maybe it was just 46 years old. There is no way to replace a chip 15 billion miles away. So they did the only thing left. They took the code that had lived on the dead chip, cut it into pieces small enough to fit in the gaps of the remaining memory, scattered those pieces around the surviving chips, and rewrote every reference so the machine could still find them. Surgery on a patient 2 days away by radio, using a manual written before the internet. They sent the first section on April 18th, 2024. 45 hours later, on April 20th, Voyager 1 reported its own health, in plain, readable engineering data for the first time in 5 months. The science instruments came back over the following weeks, all 4 of them, and barely a year after that, the team had to do it again with the thrusters. Voyager 1 keeps its antenna pointed at Earth using small thrusters, and the primary roll thrusters were slowly clogging with silicon dioxide, a residue that builds up in the fuel lines over decades. When they finish clogging, the spacecraft loses the ability to hold its aim, and a spacecraft that cannot aim cannot be heard. There was a backup set. It had been written off as dead since 2004, when 2 small heaters stopped working, and for 21 years nobody had touched it. In March 2025, engineers decided to try to wake it up. The risk was not subtle. If they fired the thrusters while the heaters were still cold, the spacecraft could be destroyed outright. The reason they moved anyway was a deadline on Earth. The only Deep Space Network dish available for parts of the work was going offline for upgrades, and after that, the window closed for months. They turned the heaters on. They waited. They fired. Thrusters dormant for 2 decades lit on command. Which brings us to the situation right now, and to the one problem no amount of engineering can solve. Voyager 1 does not run on sunlight. Out there, sunlight is useless. It runs on the heat of decaying plutonium converted to electricity, and the decay does not negotiate. At launch, the generators produced about 470 watts. Today, it is somewhere around 220, and it falls by roughly 4 watts every year. 220 watts is less than a hairdryer. It has to run the computers, the heaters that keep the fuel lines from freezing solid, the instruments, and a transmitter shouting across 15 billion miles. So NASA has been doing arithmetic and making choices. In February 2025, they shut down the cosmic ray subsystem on Voyager 1, an instrument that had been running since the Carter administration, because turning it off buys the others another year of life. The low-energy charged particle instrument was scheduled to follow. The plan is to keep retiring instruments one at a time, trading capability for calendar until only one remains. On September 5th, 2027, Voyager 1 will have been flying for 50 years. If the power budget holds, and if the thrusters keep pointing, it will pass that anniversary still transmitting, still measuring, still sending back the hum of gas between the stars from a place no other object built by humans has ever reached. Sometime in the 2030s, the last instrument goes off. After that, for a while, there will still be a carrier tone, a spacecraft saying nothing except that it exists. Then the power drops below what the transmitter needs, and the dish in the California desert hears the last of it. And the mission ends, not with a failure, but with a battery. Voyager 1 will not stop. That is the part worth sitting with. It will keep going at 17 kilometers every second in the direction of the constellation Ophiuchus, and in about 40,000 years it will pass within roughly 1.5 light years of a dim star in Camelopardalis, which is the closest it will come to anything at all. Bolted to its side is a gold-plated copper record carrying greetings in 55 languages, whale song, thunderstorms, a mother kissing her child, and Chuck Berry playing Johnny B. Good. The cover is etched with instructions for building a machine to play it, aimed at a reader who does not exist yet and probably never will. The record is designed to survive about 1 billion years in the vacuum, long enough to outlast the people who made it. Long enough, quite likely, to outlast everything they made it out of. Every scientist who signed off on that 5-year mission understood they were building something temporary. They were wrong, in the most useful way anyone has ever been wrong. And in the meantime, 49 years in, past the wall that turned out not to be a wall, a machine older than most of the people listening to it keeps whispering back what it finds. 23 hours late, at 1/10,000,000th of 1/1000,000th of a watt. Still transmitting, still measuring. Still, for a little while longer, saying something nobody expected to hear. Look up tonight, roughly toward Ophiuchus, low in the summer sky. You will see nothing. There is nothing to see. But something we built is out there, running out of power, refusing to stop talking.